Now we're going to make use of symmetry to sketch graphs in polar form. So let's say you've got a graph looking something like this. If you know it's symmetrical along the x-axis, if you know it's symmetrical along the x-axis or the polar axis, if you know it's symmetrical along the polar axis, then once you've done your first quadrant, then you can just use symmetry to sketch your second quadrant. And if you know it's symmetrical along the y-axis, if you know it's symmetrical along the y-axis, or symmetrical along theta equals pi over 2, meaning this. If you know it's symmetrical along the y-axis, then once you've done your first quadrant, then you can just reflect it, and then that will then immediately give you the other side. And also you can have what's called you can also have what's called symmetry along the origin. So you can, so this here is the origin. You can have symmetry along the origin, meaning this. Hang on, let's say you've got a graph looking like this. You can have symmetry along the origin. If you have a graph looking something like this, let's say this here, let's say this point here, the angle here, let's say it's pi over, I don't know, 7. So the radius here, let's say 6. Now symmetry along the origin means this. Well, the angle is still pi over 7. So the angle is still pi over 7. But then symmetry along the origin means, well, currently the radius is 6. Now it's negative 6. So it's like this. So there. So this point here is well, this point here gets mapped to here. If you have a point like this, hang on. If you have a point here, then let's say the angle here is whatever here. Then the angle will still be whatever, but instead of the radius being, let's say the radius here is 3. Let's say the radius here is 3. Symmetry along the origin would mean it's negative. The radius would be, the angle will still be the same, but the radius would be negative 3. So it would be negative 3 here. So this point here will get mapped to here. Well, when you see an example of it, you will get an idea of symmetry along the origin. But it's basically this point here, draw straight line. The angle here is still the same, but instead of the radius being, let's say 7, now it's negative 7, so it gets mapped to here. Well, you can make use of symmetry to save time. So once you know one quadrant, then you can use symmetry to sketch the other quadrants. So if you have if you have r equals r as a function of, if you have r as a function of theta, if you have r as a function of theta, meaning something like this, r equals 1 plus let's say cos theta. So this is r is a function, this bit here is a function of theta. So if this is the case here, then if when you apply this transformation it equals the original, then you can say it's symmetric along the x-axis. So symmetric along here. If this is the case, then you know it's symmetric along the x-axis. If this is the case, then if you apply this transformation and it equals the negative version of the original, then you can say it's symmetric along the origin. Okay? And if you apply this transformation and it equals the original, then you can say it's symmetric along the y-axis. Now I will explain this. I will explain these transformations in the next video. But if you can accept these, then skip to the example. If you find it hard to understand what's going on here, I will continue in the next video. Okay.